Hello, everybody. We are Group 6, and this is our EAPS507 project on deforestation and delving into the CO2 and temperature effects.
We chose the CO2 and temperature effects because they are one of the most prevalent and common signifiers of climate change, and we thought that they would be closely connected with deforestation levels and are easily representable on a year-to-year basis.
Next slide. Hello everyone. Our objective is to harness the power of machine learning to dissect and forecast the inherent dynamic between CO2 emissions, temperature changes, and deforestation. We are committed to delivering sophisticated models that provide not just insights but actionable prediction, aiding global efforts in forecast conservation and climate action. The heart of our mission is to pinpoint the most effective model that crystallize the complexities of these environmental factors, thus empowering policy and decision makers with the foresight needed for sustainable land stewardship. Next slide. Our project is dedicated to unraveling the intricacies connection between environmental changes and socio-economic indicators by leveraging comprehensive data set on carbon dioxide emissions and global temperature variation along with robust analytical models. We aim to forecast deforestation trends with precision. This approach not only eliminates the impact of climate variables on the forest cover but also inform strategies for sustainable management and policy development. Our ultimate goal is to contribute to preservation of our planet's vital green space through data-driven insight and actionable intelligence. Next slide.
So for such a large problem, we had to choose very high quality data. To aid us in that, we chose to source from the International Monetary Fund's climate data. Specifically, we accessed their raw data on global CO2 emission levels, mean global temperatures, and deforestations. Now, in keeping with the ethical and quality practices taught to us during this course, we have evaluated the IMF as highly reliable and ethical to use pursuant to their terms of fair use, which include the quoting of IMF contents by individuals, e.g. academics or students, for non-commercial purposes, which this project fits under. We had some data pre-preparation needed to make the data workable in an easy way for the entire team. Several steps were taken, including normalizing each data set to only have shared years for which all data had data for that year. Additionally, we needed to remove any extraneous data that might have complicated the process of scraping the data we needed from that source and converting that data from the CSV status that we received it in to workable, programmable data sets.
Our analysis has unveiled intriguing insight into environmental factors. The correlation matrix reveals a strikingly strong positive correlation between forest area and CO2 levels, implying a potential cause link where decrease in forest coverage could lead to higher CO2 emissions. Interestingly, temperature shows negligible correlation with either forest area or CO2, suggesting that within the context of our data set, temperature changes are not directly associated with deforestation or CO2 fluctuations. This analysis is pivotal in guiding future research and policy directives aimed at mitigating climate change's impacts. Next slide. Our predictive model exercise dictates the accuracy of three distinct regression algorithms in forecasting outcomes. The scatter plots compare the actual data points against the model predictions. Linear regression shows a progressive deviation from the ideal fluctuation line as the actual values increases. Polynomial regression offers a closer fit, yet with some noticeable variance at higher data values. Random forest regression demonstrates remarkable alignment with the actual values, suggesting it at the most proficient model in capturing the complex pattern on the data set. Next slide, please. In this comparative analysis of predictive models, the random forest regression emerged as a superior model, evidenced by the mean squared error of roughly 2.21 billion, significantly lower than the linear regression 6.99 billion and polynomial regressions 6.78 billion. Next slide. This is the visualization of our variable comparison. Next slide. In a comparative evaluation of data for a prediction model, the random forest regression stand out with the lowest median error and a narrow range, significantly high accuracy and consistency in its predictions. It outshines both linear and polynomial regression models, which exhibit higher median error and wider error ranges. Next slide.
So I will determine a reverse search and find out how deforestation in turn affects the CO2 levels and the temperature rise. So with the data sets given, I did a reverse search and I found out that as deforestation increases over the world, the CO2 levels have a rise and so does the temperature rise. So I used two different models. The first model I used was the random forest model with the mean squared error of 1.7 times 10 to the negative 7th exponent. So the random forest model doesn't fit the actual temperature as much as I wanted it to. And as you can see, as the actual temperature has an increase, the RF model, the random forest model, follows it, but it has many outliers and it has a high variance. Next slide, please. So over here, I use the XGBoost model, and the XGBoost has a mean squared error of around 1.6 times 10 to the negative second exponent. So over here, we can see that the XGBoost model actually fits the actual temperature data really well, and it shows a much better correlation compared to the random forest model. It doesn't have a high variance compared to the random forest model, and it doesn't have many outliers as well. However, there are some points in variance in this model, but not as much as the random forest. Next slide.
In addition to the tests conducted by my colleagues, we also utilize the Pearson, Granger, Kendall, and Spearman correlation tests. These were done on a more metacognitive level, as we found that preliminary results fit with both findings of the previous tests. However, the Granger model specifically allowed us to explore the relationship between delayed effects between various variables, as in a global context, such as climate change, direct effects sometimes take place over several years. And as you can see in the visualization below, the Granger test found that a delay of about 3 years, or lag in data terms, was most effective in correlating these variables independent of one another. And as I said in the last slide, these tests surfaced similar results to the first two, so we didn't conduct complete visual analysis of these findings. However, for the interests of thoroughness, we have included the full readouts of each test, including the Kendall, Spearman, Granger, and all pertinent statistical measures for each of those tests. In summary, we found that the analysis illustrated the robustness of all the data analysis techniques that we employed, including random forest regression over linear polynomial regression, in predicting deforestation as influenced by CO2 emissions and temperature changes, and vice versa. The random forest model's nuanced performance with the lowest error metrics reflects superior ability to handle the complexity of environmental data, whereas different statistical tests such as Granger noted the externalities and effects of time variance and delay. This study enhances our significant understanding of interplay between environmental factors and forest cover changes. It offers critical insights for policymakers, environmental planners, and for the general public consciousness knowing about this information. Thank you so much.
Yep, thank you.
Thank you.